Welcome. In this video I'll introduce incompressibility and show that in most cases, ideal MHD linear stability, the plasma is not compressed or expanded. And this is because there's a degree of freedom that the plasma can move along field lines and so minimize the change in potential energy, this delta W, which is derived in previous videos. So this delta W is the change in potential energy due to a movement or a displacement of the plasma. And we'll show here that this displacement can be chosen so that it's incompressible, so the plasma is not squashed, except at some particular surfaces, called here singular surfaces, where the perturbation is constant along field lines, and in that case there's nowhere for the plasma to go. Moving along field lines doesn't improve doesn't prevent the compression. And so these special locations, ideal MHD becomes a bit more questionable, because we're compressing the plasma, and so it's relying on this adiabatic assumption, and so this occurs at some resonant surfaces or singular surfaces. So we'll start with the delta W equation and show that by minimizing this delta W with respect to parallel flow, that we can show this incompressible. So here's the delta W equation just for the plasma. So it has 5 terms. 3 terms on the top are all stabilizing, and the 2 terms at the bottom can be either stabilizing or destabilizing, positive or negative. And one thing I pointed out previously is that all of these terms depend on the perpendicular components. So these psi perpendicular, all these, even the delta B only depends on psi perpendicular. And so the only part that psi parallel, which is the parallel part of the perturbation, so psi parallel, which is the parallel component, so along the magnetic field of the perturbation, so displacement of the plasma, and this is the only term here where it appears. And so in many cases we can choose psi parallel to make this term disappear, and because it's always stabilizing, the minimum, the most unstable mode will always have this close to 0. And so we can do this just by using the Euler-Lagrange equations, so use the variational method. I'm going to minimize delta W with respect to variations in psi parallel. And so the way we do this is just by labeling this function inside the integral. So this whole thing in here. So this is, I'm going to label L, some function of space. And we're going to write down the Euler-Lagrange equation for the variations of the delta W with respect to psi parallel, which give us d. So this is the Euler-Lagrange equation. And so we can write out what this equation is for what the terms involving psi parallel, and it's just this term here. And so we end up with the relevant bits are just so gamma p naught. So we can take this gamma p naught psi squared. So this plus an extra constant. Because none of these other components depend on psi parallel, and so we can just consider this part. And so this we can just write out as gamma p naught. And then the divergence we can write out, so we can split into 2 pieces. So one with psi perp and one with psi parallel. And so we just write that psi is just the perpendicular part plus the parallel part. And so we just write out this term here. And it helps here to then split this up in this term here with the divergence of psi parallel. And so we'll break this up into 2 pieces. And so now we can use this formula here. So this one here and take the derivatives with respect to psi parallel and gradient of psi parallel. So here we have the term following psi parallel. So if you take the partial derivative of this function with respect to psi parallel, the only term where it appears is this term here. So we have a psi parallel, so divergence of b is this bit here. And because this is symmetric, so this will have this part will also expand as a complex conjugate part. And so we end up with dl by d psi parallel. So all these terms disappear except for this one. So we just have a gamma p naught, this term here, and the divergence of psi star. And then when you expand this term out here, you'll have the same thing, just complex conjugate. And so we'll have also a term which is divergence of b, and then divergence of psi. Okay, then the second part we need is the derivative with respect to the gradient of psi parallel, so this component here. And now the only component here is just this bit here. So all the other terms don't depend on gradient of psi parallel. And so the only bit that you end up with is, and similarly when we expand out this side, we'll get the same thing, just complex conjugate. So we'll end up with a gamma p naught and then this term here, so b. So we then put these two into the Euler-Lagrange equations, and because these are just repeated, and the whole thing is linear, so we'll just take 1/2 of this, and we just consider the other half to be the same. So we can treat the real parts of this and then the imaginary parts separately. That's one way of thinking about it. But effectively, we'll just take this bit and that bit. And we can just put this into Euler-Lagrange, so we end up with, I'll just write this out here, so we get dl by d psi parallel so we get this, and then we'll put these values in, so we end up with a gamma p naught So then, next part is to expand out this term here. So we'll just expand out this whole term there, and this will break up into 3 pieces. So we end up with one which is like a gamma p naught. So we'll take the divergence of b first. And then we have another term where we take, say, the gradients of gamma p naught, for example. So you end up with b dot grad gamma p naught, and then finally we get term we have a gamma p naught. Now we're going to take the gradient of this component. B dot grad of psi, of divergence of psi. Okay, so then the left hand side obviously has this term here, and that obviously cancels with this term here. So this first term, that term cancels with that one. This term here we have a B dot grad pressure naught, so equilibrium pressure. This is equal to 0 because in equilibrium J cross grad J cross B is grad P. These are all the equilibrium quantities, and so there's no gradient of pressure along equilibrium magnetic fields, and so this term here also vanishes, and so the only term that's left is this part here. Obviously gamma p is not 0, so this bit must be equal to 0. And so therefore we have that b dot grad of divergence of psi must be equal to 0. and this is showing that it must be incompressible in most cases. So there are two ways of making this zero. So one is if the plasma is incompressible. So if b dot grad is not equal to 0, so b dot grad is not equal to 0, i.e. there's some variation along field lines. So in that case, we must have the gradient of, or divergence of psi is equal to 0, which means that if you have a wave or an oscillation, and the plasma is being compressed, so you have a magnetic field this way, for example, this is B, and we have a motion which is, say, compressing the plasma this way, so this is psi perp, and then in other locations it's like this, so psi perps, this is perpendicular to B field. What can happen is that the plasma can flow, psi parallel, which can move along the field lines, and so as plasma is compressed in this region, the plasma flows out along field lines and then out in another region. And in this case, you can have divergence of B at 0, because this flows whatever it needs to be to make the plasma go around in a circle. In some particular locations, however, you can have cases where the b dot grad is equal to 0. And so in singular surfaces, these are called. So we have the b dot grad equals 0. So this is constant along field lines. So you can see it we draw the same picture, the magnetic field, and if now I have a case where the plasma is being compressed everywhere, there's no parallel flow I can put in here which will make the plasma incompressible, because wherever the plasma goes, it's being compressed in the perpendicular direction, and so that in this case the plasma can't escape, and so it will be compressed. And so in this case you can have divergence of psi is not equal to 0, and the plasma is being compressed. This occurs, for example, in a Z pinch. Paper here, so this is a cylindrical plasma where we have a current running down the axis, so we have a current down here, and we have a magnetic field going on the outside like this. This is B field, and what can happen in a certain type of instability called a sausage instability is that these expand at some locations here and compress other locations, and so the whole surface of the plasma ends up kind of deforming like this into like a wave like this. So the whole plasma is kind of distorting like that, and this is symmetric around this way. So the whole plasma is expanding in this location and it's compressing in this location, and the magnetic field is around the plasma here. So everywhere in here the plasma is being expanded, everywhere here the plasma is being compressed, and there's no parallel flow because the magnetic field is purely in the azimuthal direction. And so in this case you get plasma compression. So this is the so-called m equals 0 sausage instability. It's partly stabilized by compression. Okay, so it does happen in some cases that this becomes important. In most cases, however, the plasma can find a way to move along field lines and minimize this term. These particular singular surfaces, these occur in tokamak plasmas, for example, where you have resonant surfaces. In this case, what happens is if you go back to delta W, the equation's near the top. So this formula here, in particular cases where this is not 0, where you have a compression of the plasma, you can see this gamma starts appearing, and this is a sign that we're including, make the assumption that we've got an adiabatic plasma, and so as soon as these surfaces appear, the ideal MHD approximations start to break down because a real plasma is not adiabatic. And so the assumptions ideal MHD become a bit more questionable in these special resonant locations.